Right, so let's see, we're in section 1.6. I believe that's right. Inverse functions. All right, so before we get into details about inverse functions, let's talk for a second about what we mean. What do we mean by when we say functions are inverse functions? What we have a function and its inverse. What does that tell us about those two functions? What are they? Yeah. They're opposite is a way to think of it. So I'm going to put this kind of an everyday way of thinking of it. By opposite, what do we mean?
Like they undo each other.
Nice. Undo each other. So that's they're opposite. They undo each other. So, for like x squared and square root of x. Whatever one does, the other undoes. And we've been using inverse functions for a long time. We just haven't, when we use them, a lot of times we don't think of them as inverse functions. But when we solve equations, what we're doing is using inverse functions. The inverse of addition, the inverse of adding 2 is subtracting 2. The inverse of multiplying by 5 is dividing by 5. The division is the inverse operation of multiplication, et cetera, et cetera. The inverse of a square function is a square root function. So we use inverse functions without even realizing it. So the idea is with an inverse function is that whatever one does to x, the other undoes. So what that means, just to make that a little more formal, we're going to say functions f and g are inverses of each other if and only if inverses have to do with compositions, if and only if f of g, which is the same as f of g of x, equals x. So whatever g does to x, f undoes, and I just get x back out. And g of f equals g of f of x equals x. So whatever f does to x, g undoes, and it just gives us back x. So we have two pieces. The composition has to work both ways. And we write f is g inverse and g is f inverse. So they're inverses of each other. So that -1 power is how we write inverse functions. So I want to just make it very explicit. F inverse is not the reciprocal of f. We mean it's the inverse function. It may turn out this way for a particular function. If f is x, the inverse function of x is 1 over x, but that's a special case. In general, you don't just take the reciprocal of a function to get its inverse. All right, so inverse functions undo each other. That means if we make the composition of one with the other, we get x back out. If we make the composition the other way around, we also get x back out. Each one undoes the other. That's what we mean by undo. So composition gives us x back. All right, we good there? Not really new and groundbreaking. Just making it more formal than maybe we've talked about it before. All right, let's talk about graphs. Anybody remember what happens or what it looks like when we graph a function and its inverse on the same set of axes? Yeah.
Is it like flipped around the x and y axis?
It's flipped and
X equals y?
there you go, y equals x. So it's reflected over the line y equals x. Very nice. Oops, over. So I just want to draw an example here. Here are my coordinate axes, and just draw an easy graph to draw. So the line y equals x is this diagonal line that goes through the origin. So that's y equals x. So if I have a graph here, like so, something like that. If this is f of x, then the inverse function would go like that. So they reflect over that line y equals x. And any graph and its inverse are going to be reflected over the line y equals x. So if you see a pair of graphs and the question asks, does the graphs represent a function and its inverse? If they reflect over the line y equals x, the answer is yes. Otherwise, the answer is no. What does that mean for a table of values? So if we had a table of values for two graphs, remember what reflecting over the line y equals x does to a table of values? Yeah, Michael?
The x coordinates and the first one are the y coordinates and the inverse.
Right, they switch. Yeah, so the table of values switch. So x's and y's switch. We could say, if we say it in terms of, instead of the x's and y's, we could say the domain and range switch. So the domain of a function is the range of the inverse. The x's and y's switch around. And that's exactly what this, when you switch the x's and y's, that's the same as reflecting over the line y equals x. So if you see a table of values, you're looking for the x's and y's to be switched on the inverse function. So if you have the pair 2, 1, the inverse function would have the pair 1, 2. They switch around. And it would be that way for every x and y. All right, so we're good with the graphs and the tables of values. So you'll have questions that involve all of these. The tables of values questions, it'll ask you in the homework, it asks to verify numerically. So you can graph them in your calculator and look at the tables of values in your calculator. So you look at the table for your two graphs, and you see that if you have an x and a y for one, that's the same as a y and an x for the other one. All right, so inverse functions have important properties. So that's what we're going to talk about next. So one-to-one functions. So if we have a graph of a function, or if we have a graph and we want to decide if it is a function, if the graph represents a function, how do we tell from a graph if the graph represents a function? Yeah?
Vertical line test.
Vertical line test. Very nice. And I'm just going to say passes VLT for vertical line test. Um, how do I want to say this? A graphed function has an inverse if, how do we tell if we have a graph of a, we have a graph, we know it's a function. How do we tell if that function has an inverse? Well, if we reflect, well, we have another way without having to graph what could be the inverse function. We have another test. The graph passes the horizontal line test. So if we have a graph of a function that passes the horizontal line test, the function has an inverse. So for example, let me just draw a quick picture here. Something like this. A nice parabola. And I'm going to say this passes the vertical line test, right? There's my vertical line. I could slide that around wherever I wanted. Passes the vertical line test. That means it's a function. But it fails the horizontal line test. Doesn't have an inverse. So that function, the function that graph represents, would not have an inverse function. What could we do to that function, to that graph, so that it would have an inverse function? Could we restrict the domain somehow? What would we do? So that it would pass the horizontal line test. Yeah?
Say that x has to be greater than 0.
Yeah, chop half of it off. I'm going to chop this half off. Well, now that half on the right, or we could chop that half off, that half on the left, would pass the horizontal line test. So we restrict the domain. So if we said x greater than or equal to 0, and we just have the right half of that blue graph, then it would pass the horizontal line test, then it would have an inverse. And I had a student in the last class say, well, wait a minute. Isn't the inverse function of y equals x squared square root of x? I said it is, but what do we have to be careful with square root of x? X has to be greater than or equal to 0. So there's a domain restriction there. It's implied. We assume it, but we've restricted the domain of that x squared function to have the inverse function be square root of x. A function with an inverse is called one-to-one. And what that means is, if we look at a table of values, we have no repeated x's or y's. For every x value, there's exactly one y value. For every y value, there's exactly one x value. And that's why inverse functions are nice. When we have a function and it's inverse, those functions are one-to-one. And we have a nice way of going back and forth from the domain to the range, from the range back to the domain. So it's always nice when we can go one way and figure out a nice way to come back the other way. It's like having sometimes functions are called maps. We have a map into into the range, or we have the same map will take us back to the domain. If a function's not one-to-one, there could be different maps that take us back to the domain. We might end up in the wrong place. Or not the wrong place, but a place we don't want to be. Another way of saying a function is one-to-one is if f of a equals f of b. So we have two of the same y values. That has to mean that a equals b. That means if we get the same y value, we have to plug the same x value in. There's no other way to get two same y values if our x values aren't the same. So we call those functions one-to-one. So a function with an inverse is called a one-to-one function. If we say a function's one-to-one, we mean it has an inverse. If we say a function has an inverse, we mean it's a one-to-one function. One-to-one functions are an important kind of functions because we can do that back and forth thing between the domain and the range. All right, so we're good with the idea of one-to-one. One-to-one is another way of saying it has an inverse. Okay, last thing for today. If we have a function, we want to be able to find an inverse. Finding the inverse functions of particular functions is kind of an important thing in math. Some functions it's hard to find their inverse. Sometimes you find a function and you use a function and it takes a while and you say, oh, wait a minute. This function is the inverse of this other function. It's a complicated function. For what we're doing, we'll have an easy way to find inverses. Does anybody remember our procedure for finding inverse functions? Yeah?
I think the first step is you switch like the x and the y.
Okay, switch x and y. Switch x's and y's. Nice. Inverse functions, when we have an inverse function, the x's and y's switch. So in our function, we're going to switch the x's and y's. The domain and the range switch. And remember the next step? So when we switch x and y, we're probably going to have x equals something, something. Yeah? Solve for y. So then we rearrange, we do some algebra, sometimes more, sometimes less, and we get y equals. And then we write, so I'm going to say this will give us y equals something. And then we write f inverse of x equals something. So instead of y equals, we just write f inverse. Just to note that we're saying that function is the inverse of the other function. What happens, I want to put one step here at the beginning. What happens if our function is written as f of x equals something? Well, there's no y's when we have f of x. What do we do? Yeah. Yeah, just write f, instead of writing f of x, f of x equals something as y equals something. So f of x is the same as y. We can change that. So don't worry about it when you see an f of x. It's the same as a y. All right, I just want to go through a couple of examples. The first one's pretty easy. The next one is the one that I particularly like. All right, so let's say we want to find the inverse of f of x equals the cube root of x minus 5. So this one's pretty easy. You might just be able to see what it is. What we call in math, solve by inspection. So what do we, just by looking at it, what do we think this is going to be? x cubed so let's think about how we'd solve an equation. To get rid of that cube, what would we do? Cube both sides, right? To get rid of that minus 5, what would we do? Add 5. So we might guess it's going to be x cubed plus 5. Well, let's do our procedure. So we're going to write this as y equals the cube root of x minus 5. And then our process is pretty much what I just described verbally. We have to switch our x's and y's first. So I'm going to write x equals the cube root of y minus 5. And then we're going to solve for y. And this is what I just described. Cube both sides. Add 5. And I'm going to change the order. X cubed plus 5. And we're done. And I write it as f inverse of x equals x cubed plus 5. Now, what would I have to do? What if the problem has asked us, find the inverse of such and such, and verify that the functions are inverses of each other? What? What? Who had? What was yours? We could graph them and see if they reflect over the line y equals x. That could work. Yeah, Michael? Right. Make the composition to verify. Well, I'm not going to do the whole process. I think we understand the process. Find f inverse of x. What should it equal? X. But we have two parts. What else would we have to do? Do the opposite order. And remember that inverse functions, it has to work both ways. F inverse of f equals x. That would be how we would verify. When you verify, you have to do the composition both ways. What would be another way to verify? Yeah. You could plug in a number for x, but that would tell you it would work for one number. We want to make sure it works for every number. Anybody have another idea? Students always do this other idea on quizzes and tests. Couldn't we just find the inverse of this and show that it's this? So we could find the inverse of 1 and then do the operation in the opposite order and show that you get back to the original thing. That would work as well. And to go the other direction, basically we would reverse our order here, essentially. This one is kind of the preferred method, but you... All right, questions on that example? Okay. Let's look at another one. This one is I like this example. This is the kind of example that teachers like. When teachers say that, that's kind of a hint. You might see this kind of problem again somewhere. And we want to find G inverse. It's not. Do you know why? You know why mathematicians are confused by weather reports? Because they think fog means compositions. Not even Friday. All right. So for this kind, students are always tempted to say, "Oh, you just do the reciprocal." It's not the reciprocal. Oh, you just change the signs, change the plus and minus. That doesn't work out quite that nicely. We have a little more work to do than that. So don't be tempted to do something that seems to make sense. Follow the process. So we're going to rewrite this. Y equals x minus 4 over x plus 2. And we're going to switch our x's and y's now. Got to switch all the x's and y's. So x equals y minus 4 over y plus 2. And now we're going to solve for y. What first step makes sense here? Multiply by y plus 2. Let's get rid of that fraction. That sounds good to me. And I'm going to write it like this. I'm going to make all these steps explicit, just so everybody sees what I'm doing. You don't have to do, you wouldn't necessarily have to do it this way, but I just want to make it explicit. So these divide and give us 1. So I get x times y plus 2 equals y minus 4. All right. Well, we still have those two y's that we have to deal with. What is our what step seems to make sense next? Anybody? Let's distribute that x. We have these parentheses. Let's distribute. That makes sense to me. So I'm going to write this as xy plus 2x equals y minus 4. Any ideas? What are we trying to isolate? What are we trying to get by itself? Y. So when you're trying to isolate a variable, what do you usually do? What if you have a bunch that variable all over the place and you're trying to get it by itself? Get them all together, right? Get all the y's together. You want them all on the same side? Well, let's do that. I'm going to subtract subtract y from both sides. So I'm going to note that below here. Minus y, and I'm going to subtract 2x from both sides. Just to get the y's all together on one side of the equation. So I have x, y minus y, not minus 4, minus y, equals, and I'm going to write this as minus 2x minus 4. This is the part where we have to be a little bit clever. Anybody see what we do? Yeah. Factor out the y. We want one y, not more than one y. Factor out that y. And now we're home free. Y equals minus 2x minus 4 over x minus 1. We've accomplished our goal, and we can write f inverse of x equals minus 2x minus 4 over x minus 1. Now at this step, if you would have gotten the y's together on the right side of the equation, this would look a little different, but it would be equivalent. Because I could factor out the negative 1 and do some various things to make it look a little different. All right, so that one's a little trickier, finding the inverse, but it's nice because we have to use some various equation solving skills. All right, questions? Okay. EOO, every other odd. There we go.